So statistics is basically organization of data, interpretation, data analysis of data to give a particular kind of outcome that you're looking for, right? Usually any form of statistics is trying to understand the hypothesis. Uh, depending on how um, what kind of hypothesis you have and how intense your result you want your result to be, you'll use different forms of statistics, right? Sometimes people limit themselves at just percentage and that's it in their surveys, which is fine if it's meeting the objective. Um, if they want to go higher than that, then you have to start using inferential statistics, right? So descriptive statistics are the collection or analysis of data, which provides you rich, detailed information about one variable, right? Not its relationship with anything else. Just one variable, it will tell you detailed amount of information that you need about it. So you'll get mean, median, mode, you can get percentage, percentile, right? About that one particular variable, variance, whatever else, right? Inferential statistics is the statistics that we use when you do higher order analysis, where you try and find relationships between two different variables, where the scores between the two different variables are different. The number of people who've answered it is different, right? So there is irregularity in the amount of data, plus it's a relationship between two different forms of data, right? So inferential statistics by design have formulas that create standardization irrespective of the length of data or the kind of data, right? Now, obviously, there are certain criteria per test that you can use within inferential statistics, but it bypasses the problem that descriptive statistics have. For example, if you have, say, if you're trying to find mean, right, and you have two variables, x and y, and one variable, everyone scores 5, 5, 5, 5, 5. There are 10 people who score 5, 5, 5, 5, 5. And then in the second variable, people score 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 9, 10, right, till 10. Now, the mean score of both of those tests will be the same. It will be 5. However, if you do an inferential statistic and you do like a t-test or something, you'll find that one has more variance than the other. One has a higher probability of a particular kind of score than the other, right? One has more significance than the other if you compare the means. That's because when you do a t-test, the formula bypasses this problem and it sort of creates probabilities, right? And therefore, they are much stronger in terms of just analysis, right? So that's the basic idea. Now, descriptive statistics will do the basic one, right? That is the central tendency, measures of central tendency. Um, Now, central tendency is the single value that attempts to describe a set of data by identifying the central positions, right? Now, there are three types of major central positions that you should know. Whereas there is the mean, which is the average of the entire variance. So you add up all the scores of everybody divided by the number of people, you get the mean, right? That is the average of the entire dispersion. Then you have median. Median is the middle score for the set that has been arranged in the order of magnitude. So if you arrange something from 0 to 100, right, then what is the middle score in that? So the 50th score, 100 divided by 250, that will be your median. Sometimes mean and median are together, sometimes they are apart, right? Then you have mode. Mode is what occurs most frequently in a data set. Okay, so this is simple enough. Standard deviation is the deviation from the mean where you can start grouping the entire variance, right? So the entire scores that you have, the entire range of scores, if you want to group them into different types as average, above average, superior, genius, whatever, or worse and below average and whatever, then you use the standard deviation score, right? That's the standard amount of deviation from the mean for this data set that allows grouping to take place. Then you have parametric and non-parametric tests. So it starts with the idea of normality. This is important. It's interesting also, right? Normality. So the definition of normality is basically when a variable is when a variable, the data in a variable is uh, the range is in such a way, right? The distribution is in such a way that most of the scores cluster around the middle, right? And then lesser towards the extremes, right? Now there are certain statistical numbers that it has to follow. So the mean in a normal distribution curve, the mean, median, and mode are the same, right? That's one important criteria you should know. So in this case, right, this 150 is your mean, it's your median, and it's your mode. It's the most occurring score, it's the middle score, and it's the average of the entire distribution. Okay. 30 scores that are 34% below the mean, scores that are 34% above the mean form the average range, right? And the average range distribution standard deviation is 50 minus 150 minus 30, 120 minus 150, right? So that's 30 and 30, right? So 150 plus 30 is 34%. 150 minus 30 is 34%. Now this standard deviation can differ from score to score. The mean score can differ from score to score, but this 34% is like a law. Now sometimes you have 33 point something and 34 point something, which is acceptable. Okay. So this is mean, 150 is mean plus one standard deviation, right? That is 180. If you go mean plus two standard deviations, then between the first standard deviation score and the second standard deviation score, the scores must be at 13.5%. Similarly, when you go backwards, that is behind. So one standard deviation below mean is 120, two standard deviations below mean is 90. 1 minus 2 is 30, and 13.5% of the scores have to be there. And then 2.35, 2.35, and then 0.15 and 0.15, right? So this is what a normal distribution curve should look like. These are the assumptions it should fulfill, right? So it's a symmetrical distribution where most of the observations cluster on the central peak, and the probabilities of values further away from the mean taper off equally on each direction. Okay. The normal distribution is an assumption. Okay. It's always an assumption, but it's at the bedrock of all statistics. The assumption is that when you analyze any population for any variable, this is the score. This is the way the scores will be arranged. There will be a lot of people from a population that will score in the middle, slightly less on either extremes, even lesser on as extreme as you go, right? So the parameters of a population fulfill the normal distribution criteria. When the parameters of a population fulfill the normal distribution criteria, then you use normal parametric tests, right? So when you are discussing parametric tests, non-parametric tests, the terms come from the idea of the parameter of the population, right? The population is assessed on certain parameters. That parameter, the basic parameter it needs to fulfill is of the normal distribution. If it fulfills it, you will use parametric forms of testing. If it doesn't fulfill it, you will use non-parametric forms of testing, right? So naturally, all of you already know that we don't assess the entire population. We assess a sample, right? So now the sample has to fulfill the parameters of the population. That means the sample collected should follow the normality curve. If it follows it, you will use parametric forms of testing. If it doesn't follow it, you will use non-parametric forms of testing. Okay. Non-parametric forms of testing. These are statistics that have been created where people have realized that it's not always that you're going to get a normal curve from a data, right? So then what do? Then they created formulas to bypass the issue of normality, bypass the assumption of normality, and still arrive at a conclusive decision, right? Statistical test that you will do is either the Kolmogorov-Smirnov test or the Shapiro-Wilk test. Okay, so assessment of normality of data is a prerequisite, right? The tests are Kolmogorov-Smirnov, Shapiro-Wilk. The Kolmogorov, oh, what the hell? Where is all this information? The Kolmogorov-Smirnov is used when the data set is above 2000. Okay, can you all see the PPT? Hello?
Yes, yes.
Yeah, okay, thank you. So the Kolmogorov-Smirnov test is used to assess normality only when the sample size is larger than 2000 units, right? If there are less than 2000 units, you always use the Shapiro-Wilk test, right? Now, this is the only place where if you have P is less than 0.5, right? If P is less than 0.5, it means that the variable is not following normal distribution. Okay, that means there is too much of significant variance here, right? Which means it's not following normality. If the probability score, which is represented by P, is above 0.05, then we will assume that the population is following normality, right? Now mug this up. This is necessary just in general for life also, but net doesn't ask it, but still mug it up, right? This is the only point where p less than 0.5 is sort of not good because you have to use non-probability methods, which is okay. Actually, it's not a problem. But yeah, so if p is significant, it means non-parametric test. If p is not significant, it means parametric test. Okay. So parametric tests are those that make assumptions about the parameters of the population distribution from which the sample is drawn. This is often the assumption that the population data are normally distributed. Non-parametric tests are not normally distributed, right? If the data deviated strongly from the assumption of parametric procedures, using the parametric procedures could lead to incorrect conclusion. In such cases, non-parametric tests are often a good option. Okay.